All right, 11.5, area and circumference of circles. I'm sure this is something you've seen before. Um, Here's what area of circle formula looks like. Here's what circumference of formula looks like for a circle. Again, you've seen those before. I think this is the first time we've actually started taking on pi. And oh man, don't get me started. I'm going to be talking about that stuff on and on. But let's get to some problems first. I mean, I think you've seen pi before. I don't think this is um, a huge surprise. The book goes into these long descriptions of how they calculated that. I think they start with the area argument. If you take the area of this, notice this is a inscribed septagon and an outside circumscribed septagon. Back in ancient Greece, they had the tools, and you saw this last time, for how to find the area of that pentagon, or sorry, that septagon, and to find the area of the outside pentagon, sorry, septagon. And you could find the difference of those. And if you look at this in Sketchpad, I can make this so that I could add or subtract sides. When if I started with an equilateral triangle, that's kind of silly. I could find the area of this triangle and the area of this triangle. I know the area of the circle is somehow in between that. But if I start to add more sides, you notice that these two areas start to get closer and closer together. I lost a side there. The area of this, now this is a nonagon. I could find the area of this nonagon if I knew the apothem and the radius of the circle, and I could find the outside one because that apothem of the outer one is the radius of the circle, and I could use trig and find this one, which of course they could do in ancient Greece, and I could find out that that's the area of those two things. In ancient Greece, they were doing this. Oh, you can't see that very well. Let me move this. They had the thing like this. Now, I did not make this document, but we could now this is Sketchpad's area of the circle. Here's a hexagon here that has 6 sides. I could change the number of sides here. This document does this for me. Right now the triangle and the circle are pretty off, but as I get closer and closer to a circle, as I add more and more sides, this thing now has, looks like 24 sides. This starts to get closer and closer to this. And if I did that with the same thing with a polygon on the outside, I know that the area of the circles between those two things. Well, they did that for centuries, you know, not really centuries. They did that long enough to sort of convince themselves. You have a polygon with 100 sides inside, a polygon with 100 sides outside. You get a really small range for what the area can possibly be, and that thing starts to get really, really close to pi r squared. No big coincidence. Another cool justification for why the area should have anything to do with the circumference. I mean, if you think about it, the pi originally was defined to be the ratio of circumference to diameter. Like, how many times does it take this to wrap around the circle? And if you start counting it, it kind of takes a little bit more than one here. It takes, like, there's a second one, and then there's a third one, and then there's this little fraction left over. It takes about 3.14 of those diameters to get around the whole circle, and that's really where pi was first discovered by people. Like, hey, this is interesting, that no matter how big I make this circle, it takes a little more than 3 of the belts to wrap around the whole thing. And what does that mean? That this is always the same? Well, it's because every circle is similar, and that constant is a fact of nature, which you've seen over and over again. But why should that same constant actually be exactly the same thing when we go to talk about area? Well, one way, can I? Oh, I can do that. One way to say, well, that's going to be the same as the area number that we need, is, well, one way to do this is chop up the area of the circle. Here it's in quarters. And lay them out like this. Now this thing kind of looks like a parallelogram. If I chop it into more and more sections, like 6 or 8, it starts to look more and more like a parallelogram. Think about what the area of this parallelogram is. The height of this parallelogram right here, this is actually the radius of the circle. If you think about these little pizza sector things, and they line them up this way, so you have one row of teeth kind of this way and the other row of teeth falling in there, so I have these 8 pieces just like this. But making them look like this, I get this wavy sort of parallelogram that has a height that is r. Now it's not exactly that height, because look at that. Of course, as you change the number of sections, that notice that height's getting closer and closer to r. Now we've got, what, 10? It's getting even closer. And what would be the, if you think about this, remember area of parallelogram, what's this length here? Well, this is, I mean, it's not exactly, but it's kind of like this little bumpy, wavy line here at the bottom of all these teeth. This is the arcs of all of the blue teeth, or green, whatever we're going to call that. If you think about that, all of these would make up half of the circumference. This is half the circumference. This is sort of R. The area, it's sort of. It's really close here, and it's really close to straight here. And again, the more sides I add, the more and more believable that looks to look like a parallelogram. Look how close that looks now, and it's just a little bit wavy. The limit at infinity here is what we talk about in calculus. This would actually be a straight line. These would be infinitely skinny. You wouldn't even be able to see them. This would actually turn into a rectangle where the height is R. But back to a more believable parallelogram. The height of that thing is R. The length of that thing is half the circumference. Well, we just learned that half the circumference was, and this is why I want to relate it to the circumference thing. This is a half of 2 pi r. Well, the half and the 2 cancel. This is pi r. So the area is base times height, which is pi times r times r. Anybody get goosebumps yet? That's pi r squared, my friends. So yeah, the area of this parallelogram has to be pi r squared, and that was the area of the circle just rearranged. Okay, so I forgot to tell you this right away. This is the stuff you're going to want to be able to do by the end of the video. Area of a circle, circumference of a circle, exact. Okay, that's a big deal. This book gets into, and as they should, the stuff about what's exact versus approximate. I'll tell you right now, when they say exact in this chapter, or when they say use pi in your answer, that means you're probably going to have a pi symbol in your answer. Don't be afraid of leaving that in the answer. So I had one on the other screen there. I'm going to do it sort of backwards here. Let's say you knew the area and you're trying to find the circumference. It's actually a little bit harder, but you know, why not? Let's say we knew the area of this circle. I'm drawing a radius there, so I'm going to need it later. Let's say I know the area is, and it's going to be some nice number because then everything else won't turn out to be nice. Let's say the area is, oh, I don't know, 70, and I'm looking for circumference. From those formulas we had, that should be all the tools you need to do those two things. The problem is, I don't know the radius. I know the area is 70. That I'm going to be able to use to figure out what the radius is. Okay, well the area is 70. That's supposed to be pi r squared. There's only one variable in this equation. It's r. It's just kind of a mess because I have a squared here and I have a pi. R squared then would be 70 divided by pi. And so r is just the square root of that, 70 divided by pi. And other than the fact that there's a square root under a fraction under a square root, that really shouldn't bother you. And I'm not done with this yet, so I'm not gonna deal with that thing for a second. The other thing is you might have in your exact answers is you might have one of those guys. Okay, so back to circumference. Circumference is 2 pi r. But I know that now. I know what r is. R is simply the square root of 70 over pi. Okay, now I kind of have to deal with this. This is all numbers now. There's no variables. I don't like this square root with a fraction in it. Of course, I said this is a lot harder than the one that you're going to have to do in the discussion tomorrow. Here we go. 2 pi times the square root of 70 over the square root of pi. I kind of want to change that so I don't have a square root of pi in the bottom. Let's make this 2 pi on top now times square root of pi. Multiply this by square root of pi over pi. I have the square root now of 70 pi over pi. Well, now I have some canceling that can happen. Great. So I have 2 times the square root of 70 pi. That's not impossible. You can have the square root of pi. Perfectly nice to answer. That one algebraically, computation-wise, was kind of a pain, but, you know, they're making this a 9th grade problem and not a 4th grade problem when you first learned about this. Okay. Let's see what else we have to do. Whoops, didn't mean to do that. Back to previous page. Exact area. The other one is revolution stuff. You realize if a wheel is going to be spinning, then every time it turns once, go to a new page. If you have a wheel and it's rolling down the road, each time it rolls once, you can think about this as I animate this. Oh, can I even do this? Sort of can't. Okay, it's going to roll down the road. Or imagine it's spinning, spinning, spinning. The amount of space it takes for this thing to make one trip around as the wheel rolls. It's like taking that. It's like if you dip this in paint or something one time, it's all going to come off once. You roll this thing once. This length from point A then it's going to roll, and it's going to end up, one revolution means point A makes all the way back around. Means the wheel has traveled the circumference of the circle. That's how far that is. So those revolution problems are really like rolling out one circumference per revolution. That's all there is to that. And back to the first page. Oh yeah, pizza deals, and lots of other stuff like this. Sometimes it might be about carpet or it might be about paint. But really, if you think about this, what we should be comparing here is area. You'd be paying for area of pizza. Area of pizza is what you eat. You care more about how much area you have rather than circumference. So there's a little bit of interpretation that has to come in these. If it's about, I don't know, buying a gold ring or something, we don't really have an area inside the ring we care about so much as the size of the circumference. So there's some word problems where you have to apply real life and think about what's more important. Is this a circumference problem? This is an area problem. Pizza price is always area. Well, I think that's about it for 11.5. It's really pretty light on the formulas. But as you know, it's going to get tougher. It gets a lot tougher next section when we start chopping up parts of circles. But for now, it's the entire circle, area and circumference.